And good afternoon. My name's Andy Holmes, and it's my great privilege to introduce the recipient of the Millie Dresselhaus Memorial Lecture, Michelle Simmons, Professor Michelle Simmons. Now, in Australia, Michelle is a legendary figure. She's director of the ARC Centre of Excellence for Quantum Computation and Communication Technology. Her research, I always regard Michelle, I think you once told me this, as the person who is willing to do the experiment that others aren't willing to do. You're willing to take the calculated risk to do that experiment, and I think her career reflects all that. She's also made many achievements. I think the most important one is powering the transition from the digital to the quantum age. But she's CEO of and founder of Silicon Quantum Computing Proprietary Limited. She was the 2018 Australian of the Year. That's a really big award. She won the 2023 Prime Minister's Prize for Science, which is also a very big award. And she is involved in developing the first quantum computer in silicon. She also gave the Boyer Lectures. Those of you who live in the UK would know that the Reith Lectures were named after the chair of the BBC at the time, and the Boyer Lectures were named after the chair of the ABC in Australia, and she gave a very interesting series of lectures there. So with that brief summary, I'd like to introduce Michelle's talk, which is called Atomic Electronics, Building Quantum Computers in Silicon with Atomic Precision. Please welcome Michelle.
Good afternoon, everyone. First of all, I'd like to say how honored I am to be the recipient of this lecture. I was very fortunate to have met Millie Dresselhaus a couple of times, and I was always struck by her incredible intellect. She was an extraordinary material scientist. And one of the things I think I had in common with her was she would always talk about the advantages of getting into a field when it hadn't yet become popular. And she said that the great thing about that was that you could fly under the radar and get a lot done. And certainly in my early career, I certainly felt that. But yes, I'm very honored to be giving this lecture in her honor. So given that this is a material science conference, the speech that I'm going to be giving is very different to what you've heard so far. But we're really trying in Australia to build a quantum computer. And I'm going to explain in a few slides what that is. But for me, probably the approach that we've taken is quite unique globally in the field, and that we started right at the outset with looking at what was the best material to build a quantum computer with. So as a person that's done a double degree in physics and chemistry, I have a strong background in materials, and in particular, looking at what materials give very, very strong quantum effects that you can not only get the highest quality qubits, but you can do it reproducibly. So if you can make one qubit and it's great, that's fine, but you need to make 1 million of them to make a quantum computer. And because they're so fragile, the manufacturing is absolutely core to actually being able to realize that system. So on this first slide, I think one thing that was kind of surprising and remains surprising to me is that we're building a computer in silicon and we're only using 2 atoms for the whole of the active components of the computer itself. So we're using phosphorus atoms, and they are our qubit states, and in particular we use both the nuclear and the electron spin of the phosphorus atom, but then we put them with precision into silicon. And it's amazing to think that just by placing them with precision and building all the component circuitry out of phosphorus in silicon, we can build the whole thing in a very clean, simple, elegant system. Now, it will be known to many of you here that phosphorus is actually right high up in the periodic table. It's right next to silicon, so it has 1 extra electron spin and 1 extra nuclear spin. And because it's so close in the periodic table, we can literally take silicon atoms out and put phosphorus atoms where we want in the crystal lattice without causing strain and without causing material interfaces. And as a consequence, we have these very high purity, clean quantum states. Over the last 25 years, that's been my mission, to see if we could build the whole computer. And what I'm going to share with you today is a little bit of an introduction as how we developed that technology with some of the key results at the beginning, and then I'll get on to the 3 products that our company is currently making. So let's just look. Silicon is an amazing material system, but the field of quantum computing is quite unusual. So every year we know that the industry, from Moore's law, makes devices smaller and faster, and it's been going for a long time, so seven decades of engineers basically every year making sure that they can maintain that law. Now, when quantum computing became a popular field in the late 1990s, at that time, most people that were doing research in quantum physics in universities were looking at what material was going to come after silicon. And so very little research in universities was actually done in the silicon material system because industry really owned that. There was so much money going into it that everybody else was looking at different materials in universities. And so they were looking at gallium arsenide or different nitrides or graphene. They were looking at materials beyond. And so what was amazing for me was when the field of quantum computing became popular experimentally, it was kicked off in the 90s when they demonstrated for the first time that they could error correct. So if there were errors on a quantum state, they could actually show that they could correct for it. And it was always believed that this would be very hard because there's something called the no cloning theorem. So to correct for errors, you have to run things in parallel and you have to actually be able to know what your system is. And in the quantum world, when you ask a system what it is, it collapses it. So somehow doing error correction seemed impossible. But in the late 90s, for the first time, they showed it was possible. And all universities that were interested in quantum physics started taking whatever material they were looking at and adapting it to see if they could make qubits, 2-level quantum states, and control information in those states. At that time, I was at the Cavendish in the UK, and we were looking at gallium arsenide materials, a very high-frequency, high-purity quantum system. And we were realizing that it was very difficult to make them reproducibly, and it was very difficult to make qubits out of them. And so at that time, I thought, well, there must be a better material. And so I was looking around all the different physical systems that are out there, and the surprising thing for me was that the material that came to the forefront was silicon. And it's kind of ironic because that was the industry material. And in the quantum world, a lot of people thought it was not ideal because it's an indirect band gap. So they thought the quantum states would not be pure. But there was already evidence to show that the coherence times of individual electrons and nuclear spins in silicon were incredibly long. So if somehow you could figure out how to manufacture with atomic precision, then you might be able to harness those long coherence times to build a scalable quantum computer. So on the right-hand side, we see some images. These are Intel images of FinFET, so conventional transistors, where every year they're getting smaller and smaller. And so at the Cavendish, the view that we had was if you wanted to get pure materials, you'd have to grow them in ultra-high vacuum in a molecular beam epitaxy system. But ideally, you'd want to be able to precision place atoms. So coming from this top-down technique with all different dielectrics, and actually 2/3 of the periodic table used to make conventional transistors, if you could somehow come from the other end and building them from the bottom up, you would leverage the purity and the single atom nature of those qubit states. So we then decided we'd take the technology that you use to image atoms, a scanning tunneling microscope, and we would adapt it to be able to put atoms in silicon with atomic precision. And that's really been the last 25 years of my life's work, and that's what I'll share with you today. But before I get there, let's just look at why quantum is supposedly better or gives you an advantage in classical computing. So a very high-level view of this. In a classical computer, you look at problems one thing after another. So if you go through code, you literally have to go sequentially through them. So if I was to write a telephone number on a piece of paper and ask you whose number it is, you would get your classical computer looking through the directory from the A's and the B's. If you wanted to go faster, you'd split the directory in 2. Faster still, you'd put 3 computers, split it into 3, and so on. But in the quantum world, you can do many calculations in parallel. And I'm a very visual person, so here's an image of what that means. We're going to use the spin states of electrons and nuclear spins in silicon as our qubits. So they can either be aligned with a magnetic field, that would be our 1 state, or against a magnetic field, that would be our 0 state. So imagine our qubit now, we're sitting in the middle of the Earth, we're either pointing to the North Pole or the South Pole. But in the quantum world, you can point to anywhere on the surface of that sphere. And when you represent that mathematically, you end up with what we call superposition. You're in some fraction, alpha 0 of the 0 state, and some fraction alpha 1 of the 1 state. So it's just a vector notation. So that's one aspect of quantum computing, this superposition. But the second one is you have entanglement. So now bring 2 qubits close together. I now have 4 separate states with 4 coefficients. So I've doubled the amount of classical information I need to describe that entangled state. But it is one state represented mathematically. And so if I do any operation on that entangled state, I essentially do it in all the individual states in parallel. And that's where the parallelism comes from. So in the qubit world, every time I add a quantum bit, I'm doubling the amount of information. But then when I'm performing operations, I'm doing them in parallel. And so the advantage of this is that if I have already just 50 qubits, it's been shown with Google back in 2018, they formed a result called quantum supremacy, where they actually found that they could get a calculation much faster using their 53 qubits than they could using a transistor, conventional transistor chip, where they'd have roughly 4 billion classical bits. And so it's that exponential power increase that the world is looking for in quantum computation. And I haven't got the applications because there are a number of applications that come out, and everyone wants to ask, I've got a slide at the end. Well, it's such an intriguing field, and there are, across multiple industries, this ability to do this kind of rapid increase in parallel computation that lots of companies have come out. And as I indicated before, unlike classical computing, where everything was pretty much in silicon, in quantum computing, we have all these different physical platforms shown on the top. So from silicon spin qubits, typically from a top-down technique, which I'll talk about in the next slide, through to ion trap systems, so capturing ions in a vacuum. Superconducting systems, that's the main US, so the Googles and the IBM use a superconducting loop of material, and they use the flux of those as qubits. You have cold atoms, which are very much like ion traps in a vacuum. There's quite a lot of work now growing in photonic qubits using single photons or something called continuous variable photons. Microsoft has been looking at something called a Majorana state, a new state of matter. And then you've got diamond systems, so people looking at diamond, defects in diamond. So suddenly now there's this incredibly rich field where everyone's trying to be the first to build a practical quantum computer that solves commercial problems. And I guess the exciting thing for us is that we got in at this field right at the beginning, and we decided that the qubit platform that we wanted, I said, would be in silicon, but we would use single atoms. So we would have the benefits of a kind of ion trap system, but in a manufacturable material, so high quality and manufacturability. So let's just look at how silicon quantum computing evolved. So back in 1998, 2 papers came out at the same time. On the left-hand side is the kind of conventional, what we call top-down technique. It's called the Loss and DiVincenzo qubit. So what they're trying to do now is to grow a hetero interface. So it could either be silicon, silicon dioxide, or silicon, silicon germanium. And then they put metal gates on the surface up here. And by applying voltages to the gates, they try and capture an electron spin at the interface underneath this gate metal. So that's a top-down kind of conventional technique. And they're basically squeezing industrial techniques and trying to push them to the very edge of actual manufacturability. So ideally, they need to get down below 5 to 10 nanometers in dimensions. On the right-hand side is an idea from Bruce Kane, who came up with the idea of using natural forming qubits. By putting the atom in place, you naturally capture the electron, and you form the qubit without this need for additional metal confinement gates. And to give you a sense of what that looks like from the top down of these devices, on the left-hand side, you've got kind of the metal that you put on the surface to try and capture the electrons underneath. And in particular, this is a 2-qubit structure shown here, where you can see you have roughly about 14 gates. And this is a recent result from Intel, where they've tried to capture 12 electrons beneath the surface, and they have roughly 75 metal gates on the surface. So typically around about 6 to 7 metal gates per qubit, which is a very, very high density. And if you try and control one qubit, you basically have metal also passing voltages onto neighboring qubits. There's a lot of crosstalk. On the right-hand side is an image of a scanning tunneling microscope image of our devices that we use in our labs. And so here, everything that's bright is phosphorus-doped silicon, and everything that's not bright is just silicon. And in these devices, we can fit up to 6 qubits in each of these dots, D1 and D2. And so now we have 6 gates for up to 12 qubits. So our gate ratio is a lot smaller. And that allows us to individually address qubits with very high accuracy without hitting neighboring qubits. And that's something I'll show you throughout the talk. So the advantage of the system we're looking at is it gives us very small systems that we can bring very close together, so we get very high speeds, very high accuracies. We can put the atoms exactly where we want, so they're very reproducible, and we have this very low gate density to qubit ratio. I guess that anyone that uses a scanning probe, and there might be some people in the audience that have tried them, a lot of people remember kind of the 1990s when they were first developed in the 1980s and 90s, and they were quite slow. And so what we've been working on is how to make devices like this, where we've got 1,024 qubits, and we can make those devices, we can pattern them in about 20 minutes. So one of the exciting things for us is the speed of manufacture. We can actually turn a chip design around from the design to the manufacture to the test in as fast as 3 days. And in the manufacturing world of silicon, that's incredibly fast, because most devices take about 16 to 40 weeks to go through a foundry. So let's hone in a little bit more about how do we actually control these systems. So here we have our phosphorus atoms, and in the original idea of Bruce Kane, he had this in a magnetic field, so that allows you to spin up and spin down states, and he had it at cryogenic temperatures, at very low temperature, so that you could distinguish between those two states without thermal energy smearing them. If you wanted to control the individual electron spin and rotate just one spin and not the neighboring spin, you would use a metal gate. In this case, he had it above the surface. We now actually bring it in plane. And you'd apply a voltage here, and that would allow you to change the amount of electron and nuclear spin overlap. It's called the hyperfine interaction. And in such a way, rather like a radio, by changing the voltage, by tuning it, you can actually tune each individual qubit into resonance in this magnetic field when you apply electron spin resonance. Likewise, you can control the nuclear spin by applying a different frequency, because nuclear spins are bigger, so they rotate at slower frequencies. If you wanted to entangle these two qubits, you have a voltage in between here that if you apply a voltage, a positive gate, it encourages the electron spins to come together, and they form this entangled state. And in such a way, you can talk from one nuclear spin through the electron spin exchange to the neighboring nuclear spin. And here's the Hamiltonian that we use for the hyperfine interaction, the nuclear and the electron spin terms. Now, the advantage of this is that that nuclear spin and the electron spin sitting in phosphorus have incredibly long coherence times. So they've now been measured up here to be 35 seconds for the nuclear spin. And to put that in context, superconducting qubits are literally microseconds to milliseconds. And here you have incredibly high control fidelities, so up to 4-9 control for the nuclear spin. As I mentioned, that very small size, it's like an atom or an ion inside a vacuum. And you've got to remember that the vacuum doesn't interact. So the quantum state stays alive for a long time. But now, instead of the vacuum, we actually use the silicon crystal as a semiconductor vacuum. So all the electrons in silicon are used to bond to each other, so there's nothing around that interacts with your qubit, which is why you get these long coherence times. I've already talked about that low gate density, but also the whole thing is epitaxial. So the phosphorus sits in that silicon site. So of course, one of the obvious things that you can look at here is you can see that these are very close together. So one of the challenges right at the beginning was, how do you actually put a phosphorus atom in a silicon crystal when you can't actually see it and know that it's there once you've placed it? Now I'll come back to this. This Coulomb potential is naturally forming qubit is critical to the success of this program because of the large energy level spacing between the quantum states. So let's look, how do we put an atom into silicon, a phosphorus atom into silicon? So we've developed a whole technique which actually is manufactured entirely in the ultra-high vacuum system. The first thing we have to do is to make some kind of marker in this silicon crystal so that when we bring it into the vacuum and use the microscope to image the surface, at the end when we take it out, we can actually find where we've put the atom. And we typically etch these in the surface. Once we've done that, we take it through to the ultra-high vacuum system. We flash it, take it to a high temperature, get rid of water and oxide on the surface, and then we cool it down under controlled conditions so we form the reconstructed surface. At that point, all the silicon atoms at the top have lost the silicon atoms above them, and so they've got a dangling bond that is not very happy. So we take hydrogen and we crack it, and that hydrogen then latches onto that dangling bond, and we completely passivate the surface, and in such a way, we form an atomic scale mask. If we come along with our STM tip, we can remove the hydrogen and expose the silicon underneath, and they look very bright. They're dangling bonds, again, sitting out of the surface, looking for something to passivate them. It's at this point that we bring in phosphine gas. This is where our phosphorus atom is coming from. It's a pH 3, it's a very small molecule. It will only absorb where the silicon is exposed, and it will bounce off the hydrogen resist layer. We then do something that I think is quite incredible. We heat the surface up, and we do a controlled chemical reaction. We can actually see the phosphorus losing all its hydrogen, and then it goes into the top layer, gets locked in with 3 bonds, and it stays there. We then take it through to the next chamber, where we have molecular beam epitaxy. We grow silicon layer by layer, and we encapsulate that at low enough temperature that the phosphorus doesn't move. We can actually image where the phosphorus is beneath the surface. And then using those registration markers, we take it out of the ultra-high vacuum through to a clean room, and we can make contact to the buried device. And this is something, like I say, we do so routinely now. We have multiple STMs making multiple device architectures every day. On the right-hand side, one of the things that's quite amazing about this is you can remove a single hydrogen atom, or you can make a wire, or you can make any shape you want. And just by changing the shape of the phosphorus, you can create capacitors, resistors, sensors, inductors, all in the silicon with just phosphorus and silicon, just by changing the shape of where you put the phosphorus. And that's quite incredible if you think about it. So now let's look, how do we get a single phosphorus in? Well, I've showed you that we're using phosphine gas, but we have to lose the hydrogen on the phosphorus, on the phosphine, before it can go into the surface. So we have to open up, a big enough hole, so we open up literally 6 pairs of hydrogen atoms. We remove those from the surface. So these are dimers on the silicon surface. And the phosphine likes to immediately lose hydrogen. Every time it loses a hydrogen, it lowers in energy until eventually it goes through an end-bridge site and it goes into silicon and actually kicks the silicon out. So you can image the surface and see the ejected silicon, so you know exactly where that phosphorus has gone in. We then pattern this in a device here. So you can see the step terraces of the silicon surface. These bright regions are now phosphorus-doped silicon, so they form conducting wires. And we pass the current through the atom, through the other side, and we try and measure the energy levels of the atom. And to do this, we have these gates either side, so we've got our beautiful potential profile, and we bias these gates to try and image the energy levels of the atom directly. I've shown you this already, so there's the 2 energy levels we expect. And if you measure now the current through the device as a function of these gate biases, you see you can load 1 electrons, and just enough 2 electrons onto this device before it goes into leakage. And so the exciting thing about this is we've done that controlled reaction. We can see where the phosphorus has gone in. And if we measure this energy level by just measuring the height of this diamond, we can tell exactly what atom it is, because we get the energy level here that matches this gap. If it was a different atom, this energy level would be different. So we can really identify electronically that the atom that we wanted has gone into the right place. And I have to admit, that was one of the most exciting points of my career to see that. We then wanted to figure out, can you make the circuitry? Can you make wires that you can bring signals down to your qubit states? And so we made these wires of thinner and thinner dimensions, so you can see they're essentially 2 dimers wide. And normally in semiconductor devices, as you make the diameter smaller, you see the resistivity of the wire shoots up. So basically that makes sense. It's got less chance of getting through, so it shoots up. And industry really struggles with that, creating heat in their conventional devices. It's so exciting. And so here, what we've done is we've put these wires beneath the surface. Because phosphine's so small, the actual overlap of the phosphorus atoms is less than a nanometer, and the bore radius is about 2. So we form these conducting wires that are very much like copper, all the way down to the atomic scale. So this was very unexpected for me. So now we realize we can put our qubits where we want. We can actually make the circuitry out of phosphorus-doped silicon. And so we wanted to see, does that reduce the overall charge noise? So one of the key things that kills any kind of qubit device is the amount of electrical noise or magnetic noise in the environment. So here we're making our devices, so our qubits are sitting in the left and right dots. We've got this charge sensor and these gates around that we use to control the electron motion in the device, and we've encapsulated it with silicon. And we now measure the charge noise. It's called the power spectral density of both the qubits themselves and of the SET, the charge sensor. And what we find is we get this incredibly low charge noise in our system, and if we actually compare that to what's seen in the literature, the value of this value of S0, it's a measure of the charge noise, is orders of magnitude lower than any other system. And this is because we only have silicon and phosphorus. We've got rid of all dielectrics, all different materials, and it's a purely crystalline device. And so that, for the qubit world, is very, very exciting. I'm now going to go in a little bit more detail about how do you measure the spin of an atom. So already to see how you put the atom in, I've given you a sense of that. But how now can you measure the spin of a single electron sitting on an atom? Certainly when I started this field, it was kind of inconceivable that you'd be able to do it. And the way that we do that is we use these charge sensors. We do something called spin-to-charge conversion. So we put our qubit states in here. We bring this device, it's called a sensor, it's a single electron transistor, and we measure the current through this device as a function of these gate voltages G1 and G2. So you can see these lines running at 45 degrees is when an electron hops on and hops off the other side. And that's the way a single electron transistor works. That's these different gaps here if I go along. When the energy level of our spin qubit is the same as the center of the island, we get this break in the conductance here, which I've zoomed in around here. So any charge movement in this device basically breaks the conduction through this sensor. And it's this around this break that we can actually detect whether it's a spin up or spin down. So I'm going to zoom in and give you just a bit of an image of how we do that. We apply voltages where we basically move up and down this line. And on the right-hand side, what you'll see is our spin up and spin down states of our qubit, our donor. Here's the energy level of that island, of the SET island. So the first thing I'll do is I'll pulse the voltages so that I will load an electron into either the spin up or spin down state. I will then, and you see what happens now as I've come off the SET, so the conductions come down. I will now pulse it, and if the energy level goes above of the spin-up state, what will happen is the spin will move onto the SET, and another electron will reload onto the donor, and I'll get this beautifully sharp peak telling me that that was a spin-up electron. And now I can pulse the voltages again, and what will happen now is that if I go high enough in energy, that electron will move back onto the SET, and I'll come back onto conductance here. So in such a way, just by pulsing the voltages of these energy scales, I can actually tell whether the electron spin was up or down. And I can do that with incredibly high accuracy. And for me, that was also exciting. And now I want to give you just a sense of why does atomic precision matter? Because most people that are making qubits haven't got the ability to see what their qubits do or to engineer them with sub-nanometer precision. So I wanted to give a sense, because this is something I've spent a long time looking at. So here's our devices. So I've already talked about that tight potential. That tight Coulomb potential allows us to get these large energy level separations. So our states are very pure. We can actually bring our sensors now very, very close to our qubits. So literally, the closer they are, the faster I can read them out. So that gives us that very fast readout speed. And there's nothing in the way. There's no dielectrics in between. It's just a nice, pure, clean silicon crystal. I can actually engineer the size of these gaps, so I can increase the current through the charge sensor. So I can make it so when the charge sensor's on, the current's very high, and when the charge sensor's off, the current goes to almost zero. And that on-off ratio gives that beautifully sharp peak. I can also make the island here very small, and the smaller it is, again, the larger the energy level separations. So I'm now really, with everything I'm doing, I'm making that readout as fast as possible. This in-plane gates is another uniqueness of our system. So I've talked about the phosphorus. It goes into the top layer of silicon. So the width of the gates is one monolayer. So it literally will address qubits that are nearby, but it will not affect qubits that are further away from it. So that's, again, something that has this very slow cross-capacitive coupling. And then the final thing here is because these gates are very skinny and very highly doped, I can actually get gigahertz frequencies down them. So all of these things combined allow us to get incredibly fast and high fidelity, highly accurate readouts from our sensors. And I guess for those in the quantum computing field, if your readout's bad, you're never going to make a computer that works. So if you get that right from the outset, then it gives you kind of an immediate advantage. So we spent a lot of time on readout. I won't go through all these results, but we're trying to figure out how to get faster. How do we get to nanosecond speeds? How do we make it more accurate? We've got lots of theoretical modeling behind it. And what we've also found out is we can change, instead of having 3 leads for a sensor, we can just create 1 lead, and we can measure up to 15 to 20 qubits with a 1 sensor. That's also something that's quite unique and something we're excited about. And then very recently, we've shown with that sensor, we can bring the operation temperature of the whole system up to 4 Kelvin. And again, the higher the temperature, generally the better the qubits. So I'll just give a couple of other things that are quite interesting about this system. Because we're making atom-based systems, we can use the STM to image the qubit directly. And so most people, when they think of an electron sitting on an atom, they imagine it's kind of a Gaussian fluffy cloud, but it's sitting inside a solid. So what it actually looks like is this. So you see the electron probability, where it sits, which is essentially where your qubit operates, is very much affected by all the bonds in the crystal. And so if you make something very small, you can actually use classical computing to measure it directly, to model it directly, to simulate it. And that allows you to work out exactly where the qubit sits. So we can start to bring two close together, and we can get all this modeling so we can predict how our qubits are going to behave. We do this in the environment of the device, so we apply electric and magnetic fields, and we found by understanding at that very atomistic level, we can take our T1 times, how long a qubit lasts, from seconds to hundreds of seconds. So we're really engineering how the electron spin interacts with all the bonds in its environment. And in such a way, you can actually start to control the spin-orbit interaction when the electron interacts with the orbits within the crystal itself. This is something that's fundamental to us to have this predictive modeling tool, and it's kind of like a quantum TCAD. The other thing we've realized very easily is that if you take all our atoms the same, and we try and hit one electron spin on a nuclear or a nuclear spin, because they're all the same, then it's quite likely that you will create rotations on the neighboring qubits. So we've realized one thing we can do is to make each qubit have a different number of phosphorus atoms. And in such a way, we can individually address all the atoms within our qubit system. So in this particular device, we have 2 phosphorus in one dot and 3 in the other dot. And by using this, we can control the interactions very easily. And we've shown that we can, with one charge sensor, individually read both of the nuclear spins and the electron spins. But we can also now load an electron on one phosphorus dot, load an electron in the opposite direction on the other phosphorus dot, apply the gate voltage to entangle them, in which case they naturally start to oscillate. And we can do it so that we bring them together, they oscillate, bring them apart, and back out again in 0.8 nanoseconds. So this is one of the fastest gates that we've seen in a qubit system. And obviously, the faster your gates and the longer your coherence times, the more calculations you can do within the time frame of the qubit. So with that kind of background, I'm now going to go into 3 types of devices that we're building, 3 types of processors that we've actually started to commercialize. So the first one is what we call an AI accelerator. And so now I'm going to kind of switch gears. Everything I've showed you now is kind of very fundamental development of the field. Now when you've got a company, we set it up in 2017, one of the most important things a company can have is customers that use your system. And so we realized for that to be real, we had to basically develop what we call the full stack. And so the full stack means that I'm no longer just sitting here playing with my STM devices. I have to figure out how to multiplex the frequencies to all the individual qubits, which means making a separate multiplexing chip. In order to get the signals that I want to run algorithms, I've got to pass long pulse sequences down to control all the gates. You imagine I'm moving my electron spins all the way around the block sphere, and the more qubits you had, the longer your pulse sequences. So I need to develop some kind of FPGA programming with onboard computers so I can actually get these pulse sequences down to the qubits. Within that, I've got to have embedded software and then control software to be able to write the algorithms. And so you've got compilers, you go all the way through to error correction and then algorithms, and eventually you make it available on the cloud. So since the company started, we've basically built all of that internally, and we have an internal cloud that we have customers using within our laboratories. And then you can run these kind of things. These are circuit diagrams. And so each one of these lines represents a qubit in time, and these operations tell you what you're doing to the qubits. You're either rotating them or entangling them, forming all kinds of different single and 2 qubit gates. So having built that full cloud access, we then started making our first 2 sets of processors available to customers. And this is the first one I wanted to share with you. It's something we're very excited about. It's in the machine learning space. So just to understand how this works, if I have pictures of cats and dogs on the left-hand side, and I wanted to be able to tell whether it was a cat or a dog, in kind of conventional machine learning, you would vectorize this, and you would pass it through some kind of random neural net. And what that typically does is it takes some number of input nodes, and it increases the number of output nodes. You're increasing the amount of data, which you then pass back through a classical machine learning tool, and it would tell you whether it was a cat or a dog. And so to give you a sense of what this kind of transition from one dimensionality to another, I've shown you these pictures on the bottom left. If I wanted to distinguish between the red and the blue dots in this R² space, it would be very hard to draw a line between them. But if I now transpose that to R³, you can see I can now put a plane between them. So by going from one dimensionality to another, I can actually start to be able to classify the data in a different way. So what we've now done is we've swapped out that random neural net with a quantum device. And it's a device that we know with this distance that it is fully quantum coherent. And I'll explain that later on in the next device that we talk about. But basically what I'm doing is I've got a strong Hamiltonian here that comes from where I put the dots in the system. I'm passing a current through from source to drain, which is essentially looking at all the different dimensionality states I have created by these 70 dots. The data that I'm taking, I actually put onto these gates, and then I basically measure the current and then change the data on the gates. And there's a process in machine learning called random kitchen sinks that allows you to translate that data. The important thing here is I'm now getting 2 to the power of 70 dimensional space. So I'm rapidly increasing the amount of dimensionality, and it's something that you cannot simulate classically. You cannot do with a classical computer. Now, to see how that works, this is just a little bit more information. We've got the Hamiltonian of the device. So you've got the hopping term as electrons hop between the different dots. You've got the on-site energy, how much energy it takes to put more electrons from one dot to another, the chemical potential, and then the Coulomb interaction terms. And I guess what's unique about this system is because we have this very low gate to qubit ratio or gate to dot ratio, we can get lots of information through this pretty quickly. And we know that the size of the device is fully quantum coherent. If we look at the results from this, we're now trying to distinguish between the orange and the purple parts of this data. And what I'm plotting here is the dimensionality versus the number of features. And where it's orange, it basically means that the quantum device outperforms a classical device. And where it's purple, it's the opposite. And where it's white, they're essentially the same. And what's surprising for us is that we see here, with sparse data sets, using this higher dimensionality, the quantum feature generator, that's what we call it, basically outperforms classical, the equivalent classical machine learning techniques. And we've done this for a series of different data sets. And what's exciting for us now is we have multiple customers using this system, and they also are seeing this with really commercial data. So whether it's, ironically, the first thing we looked at was traffic across the Sydney Harbour Bridge and trying to look for when congestion occurred. And so they have lots of cameras on the bridge, but they take data that's quite sparse. And so we were able to detect when there was a change in traffic conditions in a way that the classical computer was struggling with. So this is something we're very excited about. We've got a huge number of customers lining up for it. The second one is what we call analog simulation. And one of the nice things about our system is that precision engineering that we have means that we can start to emulate real kind of molecules and understand, for example, how current transfers through them. So to give you a sense again, this is a big field. It's booming globally at the moment. Lots of people try and simulate molecules or different chemicals using different physical qubit platforms. And so here what I show you again is our quantum dots. We can get them very, very close together. And so we can start to simulate systems that have electron fermionic systems, free electrons in the state. If you see, compared to other devices, they're much bigger typically, and as a consequence, they can't reach that kind of sub-nanometer precision state that we can with classical molecules. And so superconducting qubits are much harder, and cold atoms is another system that's also very interesting. So let's look at a typical example. Here we're looking at the polyacetylene molecule, so a carbon single and double bond repeated. We deliberately started to manufacture devices that basically simulate that directly. And we chose a system with 10 dots because we knew we could classically simulate it and compare it at the same time. And so here we have essentially 2 different devices. The main difference between the devices is whether we cut through a single bond at the end or whether we cut through a double bond at the end. In one case, we essentially form these 5 dimers that are nicely aligned, whereas the other case, we have these 2 dots that are further away. So they're different topological states. If we try and imagine what happens on this device, it's called the trivial device. As we add an electron to this system, it will basically hop through, one by one, all the way through, and you'll get a peak in the current as a function of the gate bias. And what we see here is our model and our theory, so as the experimental data. So it behaves beautifully as we would expect. On the device on the left-hand side, however, we've moved these dots further apart. So now when the electrons come into this system, the first 4 get trapped in the middle here. And so we get no current through the device until eventually the 5th electron will go coherently from one side to the other, and we'll see a peak. And that's exactly what we see. So we see this kind of double peak at the origin here, then nothing until we get the 5th electron through. So this was very exciting for us. We measured exactly what was theoretically predicted, and it meant that we could actually now start to mimic different molecules. And to get that result, there were many things we had to solve. So it didn't just happen. The first thing we had to figure out was how do we make sure that the energy levels of all the dots are more or less the same? Because if they're different, then the electrons won't flow through. And so that meant that we had to reproducibly make the dots more or less the same size, and we had to choose the ideal size so that if there was one or two phosphorus atoms different, you could still get conduction through. The second one is we literally could engineer the distance between the dots with that sub-nanometer precision to replicate a single bond and a double bond. So that's very exciting. And then the third one is this gate density. So we have these 6 gates around controlling this 10-dot system. And again, that's very hard for a lot of other platforms to do, where they have this heavy gate to dot or qubit ratio. So since that time, it's kind of your world is your oyster, because you can make any kind of shape with the devices we're making. So this is a device with 15,000 dots, and we're really starting to look at now the overlap between metallic states and insulating states, which ironically was something I did a lot when I was in Cavendish. But you can see you can make all kinds of structures in the surface. So if we just look at metallic and insulating states, we can change the actual separation of the dots, or we can change the physical size of the dots. And we can measure where they transition from metallic to insulating states. And probably the most exciting thing is here is you see the number of lattice sites and this value of U over T, and that tells you the regime of different molecules you can start to mimic. And it's very large, it's blue for our devices. So I won't go into many more details about that, but it is a unique phase space that we're in, and we're starting to look at all kinds of different effects in that space, from high temperature superconductivity to new battery materials. And then the last device or process that I'd like to talk about is the error-corrected quantum computer. So this is really where lots of groups internationally are trying to make the first practical system. And my personal view is, to get there, you need to have a high-quality system that has precision manufacturing so that you can actually replicate the same thing multiple times. And so what we see here now is on this device, there's these 1,024 qubits. We've shown that we can pattern on multiple planes, so we can have lines above and below, and we can still read out with incredibly high fidelity using these vertically separated planes. But the key thing is, to run error correction codes, you typically have to have some kind of 2D grid, so you can address qubits in parallel and synchronously. And in such a way, you can do kind of multiple operations to detect whether a qubit has occurred, whether an error has occurred on the qubit, and correct for it. So it's a very challenging field. It means you have to do lots of operations of those qubit states. But before I go to that, where we're heading with that, I'm going to show you some of our recent results, which actually are coming out this week. And so now, as I mentioned before, we're using what we call multi-nuclear spin registers. So we're not just using a single phosphorus with a single electron, but we found we can pattern multiple phosphorus atoms very close together, and we can form very efficient operations on these multi-nuclear spin systems. So let's just have a little bit of a look at that. So here again is our SET. We now have 2 dots as we had before, and in each dot we've got our nuclear spins, and then we've got our electron spins that allow us to combine 2 different registers. And as I indicated, we're showing we can get up to 6 phosphorus in each of those. And so we can rapidly scale qubit count. When we're operating a qubit now, we have circuit diagrams, and they're very much like musical manuscripts. So you see here, there are lines that run horizontally, and then each one of these lines represents a different qubit. And so we kind of have a joke with some of our devices. We actually have a musical manuscript that we will give to people about the operations we're performing on that particular device, which is fine when you're sitting below 10 qubits, but when you get to millions of qubits, that manuscript will be enormous. So it's kind of fun for now. So here you can see basically where these lines come horizontally, they're performing interactions either between qubits or an interaction on one qubit depending on the state of another qubit. And so that's what all these different operations represent, and I'll try and go through some of those to give you an idea of how you run a Grover algorithm. So let's just look. We've got, in this particular device, we've got 3 phosphorus nuclei in each of these dots. So that's 3 nuclear spins and 1 electron spin. So it's essentially a 4-qubit register. There's our electron and Zeeman terms. And so you can see now that we get, for a 3 phosphorus atom system, we get 8 different electron spin resonance frequencies, depending on the orientation of the 3 nuclear spins. So we've got a lot of electron frequencies that we take into account here. And if we move those phosphorus atoms further apart, we get different overlaps of the hyperfine interaction. And so what that allows us to do, and now we do this quite routinely, is put the phosphorus where we want to change the hyperfine interaction so we can move the frequencies far apart so they do not frequency crowd. This is an example of 2 different dots here where we've changed the value of the hyperfine. Because we've got the nuclear and electron spin, we can actually flip-flop the electron and nuclear spin. So again, there is a frequency at which we can change the electron spin depending on the nuclear spin and swap them between each other. And so just to give a sense here, Here's all our different frequencies. We can switch nuclear spin 1 with the electron by looking at these different frequencies. We can switch nuclear spin 2 with the electron, or we can switch nuclear spin 3. So we have our ESR frequencies. This effect is called electron dipole spin resonance. We have our EDSR frequencies. And so now if we want to do operations, we want to initialize the electrons and nuclear spins exactly where we want so we can perform the algorithm. So here are our 4 qubit states, our electron and our 3 nuclei. So I can now swap the electron and the nuclear spin depending on the nuclear space of the other 2 qubits shown over here. But I can do that for all the different operations of that electron spin. And that essentially forms, in the qubit world, something called a swap. We switch one electron and nuclear spin. If I now wanted to initialize all the nuclear spins in my register, the first thing I do is I initialize the electron spin down, and then I swap it with the nuclear spin. I then initialize the next electron down and swap it with the nuclear spin, and I do that over and over again until essentially at the end of this, all my nuclear spins are in the down state. So just to show you what that looks like, here are my electron and nuclear spins without me doing anything. If I look at the different occupation of all the electron nuclear spins, I've got all 8 states randomly occupied. But by forming this initialization circuit, I can get all the nuclear spins down. And now I can rotate my electron spin, and I have my electron spin qubit with all the nuclear spins down. And I find that I get very high fidelity of my electron spin qubit. But interestingly, I can do that for all the different nuclear spin configurations. So this is quite amazing. If you think about it, these phosphorus atoms are sitting within a nanometer of each other, but I can individually control all the combination of electron nuclear spins in that system. One of the things that may not be obvious to people, but during a circuit algorithm, if you read out the state of the qubit, you collapse the algorithm. So you have to form something called quantum non-demolition readout. So instead of me measuring the nuclear spins directly, I just measure the electron spins. And so by knowing the frequencies at which these nuclear spins operate out, I can initialize the electron spin, apply the frequencies, and if nothing happens and I measure it again, then I know the nuclear spins were in a certain configuration. So that's called non-demolition readout. And that allows me now to measure all the nuclear spin states. And again, we do this with very high accuracy. Once I've done that, so I can put my nuclear spins and my electron spins into any one of the configurations I like, I can then start to look at the nuclear spin qubit. And again, we're finding on the nuclear spin qubits, we're getting fidelities now above 99.9% fidelity. So these are some of the highest fidelities that have been recorded in the field. Once I've done that, I now come in with something that is totally unique to our system. Because my electron spin is overlapping multiple nuclear spins, I can perform one operation of my electron spin, and I can entangle all the nuclear spins in one go. So instead of having to do it one by one, I can entangle them in one shot, and that allows me to form these highly efficient qubit gates. And it's these efficient qubit gates that allow us to get high-fidelity 2-qubit systems, but also to start to look at different entangled states. And the way that we measure how entangled a system is we do something called Bell state tomography for a 2-qubit system, where we're getting, again, record results. And we can also look at 3-qubit entanglement, where, again, we're now getting 96%, which is the highest that's been recorded for a 3-qubit entangled state. But probably the thing that's most exciting, and that's what this result that's coming out this week is, we're now looking at the Grover algorithm. So it's one of the 2 most powerful algorithms that was originally kicked off the field, so Grover search and Shor's factorization algorithm. And what we're showing is when we run this on a 3-qubit system, we're getting this incredibly high accuracy because of this multi-nuclear spin gate. And if you compare that to the other platforms in the system, it's getting up to 98.87% of the theoretical maximum. So this is hugely exciting. It was always our vision that if we could put atoms in place and we could design the whole circuits with that sub-nanometer precision, we would be able to get the long coherence times, the fast gate operation times. We didn't anticipate the multi-qubit gate, but that's something we're finding now is fantastic for certain types of algorithms. Everything I've showed you so far is where we've put the phosphorus atoms in with that kind of nanometer precision. We're now going in and we're deliberately putting them where we want to minimize the frequency crowding. And I won't go through some of the results of that, but we're really showing that we can replicate those devices with exquisite precision. The result that hasn't come out yet, we're looking at 11-qubit systems, and we're showing that we can control all the nuclear electron spins, and again, using these multi-qubit gates on 11-qubit systems, again, above 99% fidelity. So this is something that's quite exciting in the silicon field. So I guess with that, I've just got a few minutes left. That's kind of a summary of the results of those kind of devices. What we're realizing in our system is we've got this unique ability to image where the qubits are, use that to mathematically model how the device is going to behave. We've figured out this rapid manufacturing, which we think is quite key to getting results. And we can go in, and even though you can't see the phosphorus, we can go in and control individual electron spins on atoms that are incredibly close together. One of the things that I always get asked from my whole career is how long is it going to take to build a quantum computer? And certainly it's not an easy thing to be able to predict the future. For me, the question still remains, can a quantum computer outperform a classical? And my instinct is it's right at the edge of what is humanly possible. But I also am very pragmatic, and so I myself want to know how long is it likely to take. And so what I have done is I've looked at the classical computing field on the bottom here, and I've just mapped out with the silicon industry how long it took for them to figure it out. So we can see the first transistor, 1947. It took them 11 years to get the first integrated circuit. It then took them another 6 years before they got some kind of commercial device, and at that point it was hearing aids and calculators. So it wasn't necessarily computers per se. And then 1971, another 7 years before they got the first kind of industrial semiconductor integrated computer, integrated circuit-based quantum computer, classical computer. So I've literally just taken that and mapped what we do. So, our first single atom transistor, 2012, first integrated circuit, 21, first commercially useful device, we thought it would be 28, but we think already now we have a device. So it's not an error-corrected quantum computer, but it is something we're using to enhance the accuracy of machine learning. And then I guess we're still sticking at 2033 of when you'll get the first error-corrected quantum computer. And so for a lot of the young people in the audience, I don't know if that seems long or not, but for me that is incredibly short, and it couldn't be more exciting than it is right now, to have customers using the device, but to also taste the fact that you can see how you're going to get to the end goal. And we've certainly mapped out all the different processes we need to build to get to that 2033 mark. And so with that, I'd like to thank you all for your attention. It's been a very exciting ride for me. I'm still on it. These are some of the team back in Sydney, and thank you very much.
Thank you very much, Michelle. I think you've seen that this is a person who's willing to take risks, calculated risks, and get them to work. I wonder if there are other people. We have time for a few questions.
Absolutely.
So you're happy to answer
Absolutely,
questions?
yeah.
I wonder if there are any questions. Judith.
It's a really beautiful talk. So you've given us a sort of a timeline, but I didn't hear much from you about what are the key challenges ahead, or maybe you don't really know them, but you're making amazing progress, but I wanted to hear what's going to be really hard that you can predict.
Yeah, it's a great question. So I think, honestly, when we started, we had a whole load of technical goals that we had to de-risk. And at that stage when we started, I didn't know if any of it was possible. The more I've done, the more I've realized that it seems to be working incredibly well. And so if I look ahead at the technical goals that we have, one of the key things that I think most companies have to deal with is how to get the information in and off the chip. So there is a layer of kind of classical circuitry that goes to connect to your quantum chip. And I think for most companies, that's something that has to be developed in tandem with the quantum chip. So I'd say that's probably the biggest thing that most companies are dealing with right now. With our approach, one of the things we've tried to do is to integrate the initialization, readout, control in that monolithic chip all the way through. A lot of companies are Lego blocking it, so they're doing those things in different systems and then hoping it's going to stick together. And so for us, the integratedness of our QPU, our quantum processing unit, I think is kind of, to some degree, kind of finalized. The challenges there are minimal. The biggest challenge we've got is how do we get the information in and off quickly to the qubit chip.
So that's for your company to solve that problem, is it? Or, I mean, it's not in, that information can't be gleaned from classic semiconductor companies that have got a lot of experience in that area.
No, so we're not doing that. So we're working with those companies,
right, okay.
for sure, yeah. And most people are.
Right, okay.
So that's a big field that's exploding right now.
Okay.
Yeah.
Thank you.
Thank you, Michelle, for a wonderful talk. I have a question about the silicon.
Yep.
Because, of course, silicon also has a nuclear spin.
Yes.
And I also noticed on one of your later slides, it said silicon-28.
Yes.
So do you have to make isotopically pure silicon
You do.
to do this?
You do. So when we started this project, some of the first devices, certainly the fast swap gate was in natural silicon. And so we showed that it could work, but you would see that it died pretty quickly. So you do have to get rid of, so for the audience, silicon comes naturally with 5% of silicon-29, which has spin 1/2. And so what you'll see is people now are manufacturing isotopically pure silicon-28. There's several groups around the world that are doing it. I think one of the ironies for me is when I first moved to Australia, they had a company that was making it. And so they were hoping to break into the conventional semiconductor market to reduce heat in conventional transistors, and they came at a time when the effect wasn't that great. But now there's a demand globally for isotopically pure silicon-28. And so the stuff that we show is 200 ppm in our devices. You can now start to get down to 50 ppm, 20 ppm. People are going for 2 ppm.
And conversely, though, is there any way that in principle you could harness the spin on the silicon-29?
You could, but it's random, yeah? So one of the key things for us is that precision, and we want to know exactly where things are. And so again, as a person that's been there from the beginning, when you look at a scanning tunneling microscope image of a surface, there's a lot going on. And so we had to convince ourselves that every defect, every atom on the device, we could control, and we knew exactly what was happening. And so ideally, you want to get rid of anything that you don't control in the qubit world, because you really need that exquisite precision. So yeah, we get rid of everything. So we get rid of, I wouldn't use the silicon-29 at the moment. I'm trying to get rid of it.
Yeah. Thank you. Do you want to ask a question?
Yeah. I'll give Tony some time to find your prize. Let me ask you a question while he's looking for. All right, okay. So I know quite a few people in quantum computing, and there seems to be a kind of a consensus that we actually don't know how to use them, but when they will be available, we'll find some use for them. It seems to me from your next slide that you have a different opinion and already know how the quantum computers will change the world, which seems to be not the consensus in the community.
Look, it's a great question, and honestly, as a person that's building the systems, the theoretical field about what it's going to be useful for has started with Grover's and Shaw's. Then it came up with 70 different algorithms, which are all on the US government website, and then mathematically proven algorithms. And then the question is, how realistic is it to run those algorithms with the hardware we have? And so there is, I guess, mathematically proven algorithms, which I think a lot of the theorists will agree are there. And then there's how many qubits do you need to make a commercially useful system? And there's a gap. There is a gap that I think everybody knows about. And so what people are trying to do now is bring the number of qubits you need and the hardware up to close the gap. But I think those algorithms, people agree that they're out there, but until somebody does it, no one knows, yeah? So it's for me, the question is, can it be built? Can it be used? What are you going to use it for? What are you going to use it for? The algorithms are there, but we've got to get enough high-quality qubits to run it. And I guess for any research field, the only way to know is to do it. Do you know what I mean? So you actually have to build the systems and try them. There was a question up the back.
There's one at the back, and then one in the white shirt. One at the back first. Oh.
Yep.
Thank you, Michelle, very much. About the nuclear spin.
Yes.
Can it be controlled by the size of the dot, the number of atoms that you include in the dot?
Yeah, so at the moment, like I say, we've controlled 6 different nuclear spins in one dot. We've not gone higher. So with the 6, at the beginning, honestly, we were not expecting to control that many because we thought there'd be frequency crowding, but because we can place them, we can minimize that. So we haven't yet reached the limit of what we can control. We're just increasing to see at the moment.
Okay, thank you.
What is the distance between 2 phosphorus atoms that 2 phosphorus atoms spins can couple and make triplet state. So what may be the maximum distance?
Yeah, it's a great question. So we're literally looking at the electron interaction, the nuclear spin interaction as a function of distance. So we can bring them within like literally 2 bonds of each other. And so what we're doing at the moment is working out what those different coupling terms are for both the nuclear and electron spin. But typically at the moment our devices, they're about 1.5 nanometers, and we don't see that interaction occurring. We have to load the electron to get the interaction.
I have a question about the gate geometry. How do you manage that in terms of these dots are so close?
Yeah, well, so I don't know if you saw, but our gate, so our dots are about 12 nanometers apart, and our width of our gate can be 10 nanometers. It goes all the way down to 1, but even with 10, we can control individually the 2 from one lead. So yeah, so what we're doing now is literally figuring out how can we reduce the density of leads so we can measure more and more qubits.
Right.
And we can go all the way down. So 10, we're doing 10 at the moment, but you can go all the way down to 2. Right. So yeah, I don't know how to describe it. You can literally change the dimensions of everything, and we're literally making and measuring constantly to model it.
I was struck by Tony's question as thinking the great breakthrough in silicon semiconductor fields was the purity of the silicon, and now you're talking about the next stage.
We're leveraging that decades of work.
Yeah.
And I think that's something I also believe. If you've never manufactured something at scale in a material, you don't know that you can do it. Yeah. So the good thing about silicon is we know that people have manufactured, millions of transistors. So and we're making things much smaller. So it's just a question of how pure is it now for our small systems.
Well, I think at this stage we should ask Sir Tony to come up and make a presentation to you, Michelle. But let's just thank Michelle for a wonderful lecture.
That was absolutely, well, I'll speak into the mic. That was a sensational talk, Michelle. And I've heard a lot about your work, but I don't think I've ever heard you speak on it before. So Thank you so much. And it's a fitting way to remember Millie Dresselhaus, who loved to come here and came year after year until 2017. And I was worried about the location of the plaque, but it's hidden from where I was sitting down there. So it's actually here. And so it gives me great pleasure on behalf of RACCAM and the IWAM community to present you with this wonderful plaque.
That's lovely. Thank you.
And do we have a photographer?
I think that's great.